Hello friends. So today we are going to discuss four questions, and these four questions will be based on the conservation of the momentum as well as our energy. And so in the first question we are given that, and these questions are pretty simple, not much of basic questions are there. So in the first question we are given that consider a one-dimensional head-on elastic collision between two particles. A particle of mass 2m moves to the right with a speed v, while a particle of mass m moves to the left with the same speed v. After the collision, determine the final velocities of both particles in laboratory frame. Solve the problem using the following approaches. And so basically we are going to solve it by two methods which are mentioned in the question itself. First is by applying conservation of law directly in the laboratory frame, and the part second by transforming to the center of mass frame, then converting the result back to the laboratory frame. Okay, the same question we can solve by using two methods, and it's a pretty straightforward based on our conservation. Okay, so not much of you can say trouble will be in solving these questions. And so we can say that if we are having two masses, we have a mass of 2m, and let us suppose its initial velocity is our u1, and it is moving with plus v direction, plus v velocity. Okay. So in this case we are assuming towards the right is our positive, and then we have second mass, and that mass is of m, and this initial velocity is, let us suppose, our u2, and it is moving in opposite with the same speed, that is minus of v, and we are given that the collision is elastic. So first part A is our in the lab frame, and part B we are going to start with center of mass frame and then transform back to the laboratory frame. So we start with our part A. And in this part A, the solution in the lab frame. So we are going to use the conservation of momentum. Conservation of momentum, and okay, here let us assume their final velocity also, that will help us. So final velocity of our mass 2m is, let us suppose, our v1, and for our mass m is, let us suppose, our v2. Okay, so these two are our final velocities. So for the conservation of momentum, we have our initial momentum will be equal to final momentum. So So initial momentum will be equal to about 2m plus of v and plus m minus of v, and that will equal to final momentum, that is twice m and sorry, it is m, not m1, twice m times v1 plus m times v2. And right side we can solve it. So we are going to get that as our, we can cancel out this m throughout. So we get this as m v1 plus v2 will be equal to, or twice v1 plus v2. So we can write this as our twice v1 plus v2 is equal to v. So this is the first equation. Then we can use our conservation of energy. Conservation of energy, and our initial energy will be equal to our final energy. So our initial energy will be equal to half 2m v square plus half m v square is equal to, and half 2m v1 square plus half m v2 square. And here we can one second. Okay. So we can solve it, and we can cancel out this m throughout, and we can also cancel this half throughout. So we get this as our 3v square is equal to twice v1 square plus v2 square. Okay. And this is our second equation. So we have a first equation as well as our second equation, and from first equation we are going to find out our v2. So from here we can say that our v2 will be equal to our v minus twice of v1, and we are going to substitute this into our second equation. Therefore we can say that our we can write this as our 3 by 2 v square is equal to our v1 square plus, and this comes as our half, and v minus twice v1 whole square. And now it is simple mathematics to solve it. So we get this as our v1 square plus half v square plus 4 v1 square minus 4 v1. And okay, so we can further write it as this we can multiply by 2, so this comes as 3v2 square 2v1 plus v square plus 4v1 square minus 4v1 not equal to 0. And furthermore, we can combine the terms, so this comes as 3v square, and this is also v square, giving us 2v square. And we have here 2v1 square, and this is our v1 square, so this will be giving us 6v1 square. Okay, so we can write this as our 2v2 square minus 6v1 square plus 4v1 is equal to 0. And let us make it a quadratic with respect to v1. So we can take 2 as common along with this negative sign, so this comes as 3v1 square minus twice v1, and this comes as minus v square. From here we can find out our v1. Okay, so we are going to have two values of v1. Either our v1 will be equal to v, or our v1 will be equal to minus v upon 3. And if the velocity, if v1 is equal to v, then we can say that there will be no possibility of the collision. Okay, so we are going to simply discard this part, and we are going to take that our v1 is equal to minus v upon 3. Okay. And now we can easily find out our v2. So v2 was our v minus twice v1. So v minus twice v1 is equal to v minus twice minus v by 3. So we get our v2 is equal to, this will be coming as minus minus plus, so this will be a 5 v by 3. So we have our v1 v by 3 and v2 is equal to 5 v by 3. And this we solved in our lab frame. Same problem we are going to solve by using, rather we can say we are going to start with center of mass frame, then we are going to again shift to the lab frame. Okay. So this is a center of mass frame. So we are going to find out the velocity of the center of mass. You can see our center of mass velocity, that is our VCM, and that will be equal to our first mass, its velocity, plus second mass, its velocity, and our total mass. So here this m cancels out throughout, and this comes as our v by 2, v by 3 rather. Okay, because this is 1, so this will be coming as v by 3. And we have two masses, 2m as well as m. So respectively, we are going to find out their velocities in the center of mass frame. So you can say the velocities in center of mass frame. So we are going to start with first mass. First mass is our 2m, and let us suppose its velocity is our u1 prime. So this u1 prime will be equal to our v minus v by 3, which will be giving us 2v upon 3. And other mass is our m. So for this m, let us suppose we call this velocity as v2 prime. We call this a velocity as u2 prime, and that will equal to minus v minus of the center of mass, which gives us minus 4 by 3 times v. So we found out the respective velocities of mass 2m as well as m in the center of mass frame. And the collision is said to be ever elastic. So we are given that we are having elastic collision. So because of this elastic collision in center of mass, the velocities are going to reverse the direction after the collision. So we can say that because of this elastic collision in center of mass frame, the velocities reverse directions. Therefore, we can write that our E1 prime will be having a minus 2 v by 3 and our E2 prime is going to have plus 4 v by 3. Now we are going to convert this into again to the lab frame. So transform back to lab frame, and obviously everything we calculated previously was because of the center of mass velocity, and that will be respectively added to each mass. So we start with the mass 2m, so which gives us that v1 will be equal to minus 2v by 3 and added the velocity of center of mass, that is our v by 3. So this gives us minus v by 3. And then we have mass m, its velocity is our v2, and that is our plus 4 v by 3, and this will be plus v by 3. So this gives us 5 by 3 times v. Okay. So in both the methods, we found out that the velocities are going to remain same. Okay, whether we deal with it in the laboratory frame or we solve it at the start with the center of mass frame, then convert back to the lab frame. So either way, we can find out the results are going to remain same. So this is just a basic understanding, otherwise these questions are not so much typical. Next question. So it is given a particle of mass m moving with the initial speed v undergoes an elastic collision with a stationary particle of mass 2m. After the collision, their velocities are v1 for mass m, v2 for mass 2m. Show that the velocity v2 is perpendicular to the vector v2 plus twice v1. Okay, so we have to prove the perpendicularity, and for that we can use the property of our dot product. Okay, ultimately we have in the last we are going to use that. So we are given that we are having a mass m and it is moving with a velocity v, and we are having mass 2m which is our stationary. Okay. And after collision, our mass m, it moves with the velocity of v1, and our 2m, it moves with the velocity of v2. So once again we are going to use the conservation of energy as well as the momentum. So we have conservation of momentum, so initial momentum is only because of mass m, so that will be equal to over m times v, and final momentum will be because of both the masses, that is m v1 plus twice m v2, and here m cancels out, so we get v is equal to v1 plus twice v2. Then we come to our conservation of energy, that is our conservation of kinetic energy. Conservation of our kinetic energy, and initial kinetic energy is our half m v square, and final will be our half m v1 square plus half 2m and v2 square, and this half along with this m cancel out throughout, therefore we get that v square is equal to v1 square plus v2 square, and we are going to square this equation, so we get, we are going to square momentum equation because this is already squared. So let us see equation number 1, this is equation number 2. So from equation 1, squaring equation 1, we get v square is equal to v1 plus twice v2 whole square, which is giving us v1 square plus 4 v2 square plus 4 v1 v2, and we are going to eliminate our this v square. So in place of v square we are going to put equation number 2. So we get this as our v1 square plus v2 square is equal to v1 square plus 4 v2 square and 4 v1 v2, and our v1 cancels out, therefore we get as one second, I missed something. Yes, I missed here 2. So from here we can combine these two terms, and this gives us minus 2 v2 square is equal to 4 v1 v2, and we can also divide by 2, so we get this as minus v2 square is equal to twice v1 v2. Okay, here I forgot to mention one thing, that all these velocities are in the vectored form. Okay, these all are in the vectored form. So all these are in vectored form. Therefore, we can write that this will be equal to our v2 dot v2 plus twice v1 v2 is equal to 0. So from here we can take v2 as common, so we can write our v2, and it will be coming as v2 plus twice v1 is equal to 0, which basically means that they are perpendicular to each other, okay, because their dot product is equal to 0. Therefore, you can say our V2 is perpendicular to our V2 plus twice V1. That was the question. Next question. It states that n identical balls are constrained to move along a single straight line and undergoes only elastic collision with one another. You are free to choose their initial velocities arbitrarily. What is the maximum possible number of collisions that can occur among the balls? We have to find out the maximum number of collisions that are going to take place. Okay. And in this case, because they are moving in the single straight line, so the collision is only possible if the velocity of left ball is faster than the right ball. Okay. You can say that collision between two balls occurs only if the left ball is moving faster than right ball. So your left and right means that suppose we have a ball in the right position. Okay, so this is a right position ball and we have ball which is in left position. So collision is going to take place if the velocity of this left ball is greater than velocity of our right ball. Then they are going to collide with each other. Otherwise they are not. Okay. And therefore we can say that our another thing, that after elastic collision, the relative order of velocity of two balls are going to reverse. Okay, then we can, and secondary thing is that after elastic collision, the relative order of velocities of two balls reverses. And therefore we can say that each collision removes one inversion in the ordering of the velocity. So from here we can just draw a conclusion that our each collision removes one inversion in the ordering of the velocity. In the ordering of the velocity. So we are going to solve in general for two particles, and that can be extended to n number of particles. So we can start with the two particles. And we consider these particles, or let us say two balls. And these two balls are I and J, and I ball is having mass Mi and J ball is having mass Mj, and their initial velocities of Mi is our Ui and of Mj is our Uj. So these are our initial velocities, and Vi and Vj, these are the final velocities. And now we can use the momentum conservation. And for momentum conservation we can write that Mi Ui plus Mj Uj is equal to Mi Vi plus Mj Vj. And then we can write the energy conservation. And that will be equal to over half Mi Ui square plus half Mj Uj square is equal to over half Mi Vi square plus half Mj Vj square. And we already know that whenever there is an elastic collision between two bodies, these solution of these two equations are going to give us a standard result, and that standard result is that our Vi minus Vj is equal to minus of Ui minus n Uj. This is a standard relationship, or we can result by solving these two equations, equation number 1 as well as equation number 2. And from here we can say that the relative velocity reverse sign after the collision, because Vi minus Vj is the relative velocity after collision and Ui minus Uj is the relative velocity before collision. Therefore from here we can say that a relative velocity reverse sign after collision. Okay. So it means the faster particles become slower than the other after collision. So this is another conclusion which we can draw from here. So you can say the faster particle becomes slower than the other after collision. So these are the two important conclusions which we can draw from this particular solution. Now if there are, you can say, balls which are spaced with respect to distance x1, x2 up till xn. So based on this, let us find out the condition for a collision. Condition for a collision. And for that we say let the balls be ordered in space as, so we can write that our x1 is our leftmost, then it is x2, then it's x3, and so on up till xn. So nth ball is our the rightmost and x1 is our leftmost. And so we can say that the collision between the balls I and j collision between balls I and j, and obviously we can find out the j with respect to our I, so we can say our j will be nothing but our I plus 1. Okay, that is the very next ball. The collision between the balls I and j can occur only if our u of I is greater than u of j, or we can write this as our u of I is greater than our u of I plus 1. Okay, so this velocity equation should hold. Okay, otherwise the left ball never catches the right one. Okay. And here we defined, or we try to understand one term, that is our inversion. Okay. So we are going to discuss same but with respect to these velocities. So you can say velocity ordering and inversions. Ordering and inversions. So we can define our inversion number. We can say velocity inversion number that is our I will be equal to, and that depends upon our I j for the condition that our I is following our j and u of I should be greater than our u of j. Okay. For this condition we are going to get the velocity inversion which we have defined our I. Okay. So it means that we have two balls. This is our I ball and this is our j ball. So I should be behind our j, but the velocity of our I should be greater than velocity of our j. Then only a collision is going to take place between the two balls I as well as j. Okay. And this, you can say, this counts how many out of order velocity pairs exist initially. Okay. We will discuss that later on also, but right now we are more interested in this velocity inversion number. Okay. So it means if there is one collision, so we can say that our effect of one collision on inversion. So it means, like I said, we have two balls and we have a ball I, and it is going to collide with the ball j, and j we can also write that our I is going to collide with the next ball, that is our I plus 1. Okay. And this we said is only possible if our u of I is greater than our u of I plus 1. And for our this elastic collision, like we said, that the velocities are going to interchange. Okay. 1 second, here we wrote, yeah, the velocities of the two balls reverses. Okay, therefore we can write that our after collision velocity, we can write that our v of I will be less than v of I plus 1. Okay. So it means one inversion is removed with one collision. Okay. So from here we can derive a conclusion that we have exactly one inversion is removed and within this specific set we can also write no new inversion can be created. No new inversion can be created. So it means each collision decreases the inversion by only one factor. So final conclusion based on this two, we can write that our each collision decreases the inversion factor, which is our I, by exactly 1. So based on this, we are going to find out what will be the maximum possible initial inversions. Okay, we know one collision is going to reduce the this inversion by 1, and then we are going to find out that maximum possible initial inversions. And we have total number of n objects, and these inversions are observed if their velocities are strictly decreasing. Okay. Because we see that their velocities are strictly decreasing. Okay. And we can write same term using with respect to our initial velocity also. So we can say that the maximum number of inversion among n objects is obtained when velocities are strictly decreasing. Or in terms of the equation, we can write that the velocities of our u1 should be greater than velocity of u2, should be greater than velocity of u3, and so on, should be greater than velocity of our un. Okay. So under this condition only, the maximum inversions are going to take place, because inversion is related to our collision. Okay, we just proved here that each collision decreases the inversion by exactly one factor. So it means whenever there will be collision, the inversion will be reduced. So maximum inversions will be only possible if the velocity of our left, you can say, particle is greater than our right particle. Okay, so left particle means placed in left position and right particle means placed in right position. So the collision is going to take place if the velocity of this u1 is greater than velocity of u2. Okay, so this is the important part here, that this condition is to be fulfilled with respect to their velocities. And from here we can write that our maximum inversion, that is our I max, we can write it in the formation that our n of 2, or we can write this also as our n minus 1 divided by 2. Okay, so this condition is to be fulfilled so that we are having maximum number of inversions. And from here we can also find out the upper bound on the number of collisions. Upper bound on number of collisions. And so the upper bound will be defined as the total number of collisions so you can say that total number of collisions should be less than equal to our maximum inversions, or in place of maximum inversion we can put its equation n minus 1 divided by 2. So this is our third question, I think. And we come to our next question. This was the last one. No, one more is there. Okay. Now this is quite simple one. Not much of thing is required. Only the statement is quite big. Otherwise, the solution is much smaller than the statement itself. A pool ball moving with the initial speed v is aimed exactly midway between two identical stationary pool balls. After the collision, the two initially stationary balls move off symmetrically at angle plus 30 and minus 30 with respect to the original direction of the motion. Determine the final speeds of all three balls after collision. Assume the balls are identical and all collisions are perfectly elastic. So this question is quite simple. Suppose we are having three balls. And this is our ball number A, and then we are having two balls which are lying something like this. So this is ball number B and this is ball number C. And after collision, with respect to the original direction, ball B moves at an angle of 30 degree and ball C also moves at angle of 30 degree. Okay, so this is ball B and ball C. And let us assume that the velocity of ball A after collision is u. Okay, so let us assume that initial velocity of ball A velocity of ball A is our v, and final velocity of ball A is our u, that is our after collision. And for this B and C, these are, you can say, by symmetry, we can say that initially both are at rest, so we are only interested in their final velocity. So we can say final velocity of B and C. So we can write that velocity of B magnitude wise will be equal to velocity of C, and let us suppose that is equal to some variable, that is of W. Okay. And so we are going to use the conservation of momentum and the initial momentum only ball A is moving in x direction, so we can say our P of I is equal to our mv x unit vector. And then is our final momentum, and final momentum we can divide into the components. So this is our B at angle of 30, so it is going to have two components, and their velocity is our W, so this comes as W cos 30 and this comes W sin 30, and then we having our C, so once again two components, W sin 30 and we have W cos 30. So the vertical component will be our 0. So final momentum for B and C. So we can say in y direction we can write that our omega sine 30 plus omega sine 30 will be equal to 0. So you can say m omega sine 30 minus m omega sine 30 is equal to 0. So it means for our ball A, its momentum in y direction should be also equal to 0. So we can say for ball A, its momentum in y direction should be also equal to 0, or we can say that the velocity of A in y direction will be equal to 0. So it means ball continues to move in x direction, along x-axis, not x direction. So we can say that ball A continues to move along x-axis. Okay. So we solved for y direction, now we come to our x direction. And initial momentum will equal to final momentum. So initial momentum was our m times v, and final momentum is our mu plus mw cos 30 plus mw cos 30, and this m goes out throughout. Therefore from here we can write that our v is equal to u plus square root of 3 times w. And now we come to our kinetic energy. You can say energy conservation. And for energy conservation we can say our initial energy was equal to over half m v square, and the final kinetic energy is over half m u square plus twice half m omega square, and here this half m cancels out throughout. Therefore from here we get that v square is equal to u square plus twice w square. And we have two equations. Let us put this equation number 1 and this is equation number 2. So if we solve these two equations, equation number 1 and equation number 2, we are going to get the value of u as well as w. So you can say from equation 1 and 2, this gives us that our w is equal to 2 root 3 divided by 5 times v, and we get the u is equal to minus 1 by 5 times v. Okay, so only negative sign mean that our this a will be moving in our reverse direction. So these were 4 questions, and today's question, except one in which we discussed the inversion part, rest of the question was comparatively quite easy, but somewhat basic concept we use. Okay, so this completes today's 4 questions. Thank you.